Chapter 9, Wave Interactions. Section 9.1, Interference of waves, constructive and destructive interference. When two or more waves come together, the particles move up and down and allow the waves to pass through each other. The waves are not modified, so the amount of energy stays the same. Thus, when two or more waves interact, the particle vibration is such that the direction and energy of each wave is preserved. When two waves meet, the forces on their particles are added together, and the way by which they are added is governed by the principle of superposition. And the principle of superposition states, at any point, the amplitude of two interfering waves is the sum of the amplitudes of the individual waves. The wave interference can result in constructive interference. This is the process of forming a wave with a larger amplitude when two or more waves combine. Here we have two crests of a transverse wave that are approaching each other through the same medium and are about to interact with each other. One of them has an amplitude of 1 unit, and the other has an amplitude of 2 units. When these two interact with each other, the principle of superposition states that the resulting interference pattern will result in a wave whose amplitude is equal to the sum. And we can see in the diagram that the interfering wave pattern is a supercrest whose amplitude is 3 units, the sum of 1 and 2 units. This could also happen with troughs, where two troughs interact with each other to produce a supertrough. When the interference pattern is done, the result is that the waves continue to move past each other with their original amplitudes, original direction, as if they hadn't interacted at all. Now, destructive interference can occur, and this is the process by which the forming of a wave with a smaller amplitude when two or more waves combine. In this example, we see a crest whose amplitude is 2 units, that is 2 units above the equilibrium or rest position, is approached by a trough whose amplitude is negative 1 unit or 1 unit below the equilibrium position. When these two waves interact with each other, the resulting interference pattern is equal to the sum of the two amplitudes of the original waves. So if we have 2 units above and 1 unit below, plus 2 and minus 1 equals plus 1. We end up with a crest whose amplitude is 1 unit, the sum of the original amplitudes. When the interference is done, the two pulses continue past each other with their original amplitude and original energy intact, traveling in the same original direction. Let's take a look at a slightly more complex example. I'm going to color code these. I'll leave one of the pulses in orange, and I'll make the other pulse a blue color. So here we have a crest whose shape resembles a rectangle, about to pass over a trough whose shape resembles a slanted triangle. When the two are over each other, we can predict the resulting interference pattern by finding the sum of the individual amplitudes at each particular point. And I'm going to break up this section into a bunch of different points, 2, 3, 4, and 5. At point number 1, the orange wave has an amplitude of +2, and the blue wave has an amplitude of -2. When you add these two together, the resulting displacement of +2 minus 2 is 1. And our wave interference will look like this. At point number 2, we can see that the orange wave has a displacement of 2 units above, and the purple, or blue rather, has a displacement of 1.5 below. If we add +2 and minus 1.5, we will get a resulting interference point whose displacement is 0.5 above the equilibrium position. Let's then find the sum at point 3, where we have 2 units above and 1 unit below. That resulting interference pattern, +2 minus 1, is +1. So we have a resulting interference point that is 1 unit above. At point number 4, we can see that we have the orange wave has a displacement of 2 units above, whereas the blue wave has a displacement of 0.5 below. So 2 minus 0.5, we get a resulting interference point that is 1.5 above. At point number 5, we can see that the orange wave is still 2 above, while at this point the blue wave has a displacement of 0. So 2 plus 0 results in an interference point that is 2 units above. So I'm going to trace this over, and I'm going to use a little thicker line so that we can see it. When these two waves, when this rectangular crest approaches this triangular trough, the result will be a displacement or interference pattern that looks like this. Okay, I want you to try 2 examples. I've left you some graph paper below. I want to try to see what the interference pattern will be when a crest that looks like this overlaps a trough that looks like this. Let me make this a little bit more clear. When these two overlap, what will the resulting interference pattern look like? Similarly, I want to try a crest like this approaching another crest that looks like this. When these two overlap each other, what will the resulting interference pattern look like? For the first example, if you use the principle of superposition and find the displacements of these points, your answer should look like this. And in the second example, we have total constructive interference, so our interference pattern will look like this. Try the homework questions listed below and any LMS quizzes on this section. Good luck.